So as we're taking derivatives of functions, we're going to reach spots where we can't evaluate the derivative. And part of that's going to tie to continuity of the function. And a fun way to think about this is relating it to roller coasters. Having a roller coaster that's fun and safe to ride. So let's say we're going to design a new roller coaster for Cedar Point, but we need to make sure that it is both fun and safe. So which roller coasters meet? Let's add that. Both requirements. So what do you think makes a roller coaster fun to ride? Well, we should probably have motion. We should be moving. So as time's passing, our distance should be changing. We want some dips. We want some increases. And some steep dips are fun. And kind of high climbs are good. So with that, we're thinking, let's say, climbs and dips and moving. That should be a basic one, is that we're moving somewhere, but those kind of ideas. What makes a roller coaster safe to ride? And how I think I would describe it, and maybe you would have different terminology here, but I'm thinking of kind of smoothness, a smoothness to the ride, where it's not suddenly jerking you in one direction or another. Some scenarios we'll see. You shouldn't be hitting a wall of any sort. The roller coaster should be all connected. It shouldn't be jumping at all. So that idea of jumping should have you thinking about discontinuities a little bit, but we'd want this smooth ride. So how this is tying with continuity is this idea of, if I draw a function, I should be drawing the whole thing without lifting my pencil up, and that makes for a nice fun roller coaster ride. What we don't want are scenarios where we make jumps. We also don't want any sharp edges. So for each roller coaster design below, mark the point that is most thrilling, what's the most fun part of the ride, and then determine if the roller coaster is safe to ride and explain. So this first one here, so we can see we're climbing up, and then we have the dip, and then we climb up again, and then another dip, and then we climb up again. So I think the most fun parts is where you're descending, and probably the most fun is where you're descending the fastest. So it might be kind of hard to see. It looks like the rate of change, it might be pretty similar here actually. I'm looking kind of in those areas and thinking about the tangent line. And what I'm looking for is which one is the most steep. But those look pretty even. Maybe that first one's a little more steep, but let's go with both of those. Those look like equally fun parts to me. Now, we could be seeing like a steepness here. I don't know if the climb is really the fun part of the ride. I think the kind of falling downward part is the most fun for me personally. So with that, those look fun. But as an idea, we wouldn't want to be going too steep. Like, you wouldn't want to climb up and then be dropping like that, because, that might be like you're falling off a cliff, and that's not fun. So we want this kind of smooth ride out of it too as we hit those dips. So that one looks great. It also looks safe because as we have the descent, we then come out of it in a smooth way. So it's not suddenly jerking us to go upward all of a sudden. We kind of ride out of those curves. So this one looks fun and safe to me. Let's take a look at this next one. So with this one, we're increasing up, we hit our height, and then all of a sudden dip down. That's the best way I can describe this. That sharp change, it's not terrible. It might even be a little fun. I don't know about safety though. So something we're going to talk about is a sharp change like this. The derivative here is not defined at that coordinate. So we can't find the instantaneous rate of change there because we technically have two rates of change. We have a rate of change that's going upward, and we have a rate of change that's going downward from the left side to right side. So we want to be careful there. What would have been better is if that had smoothed out and we had a nice curvature to then dip down, something like that. So this one, it might be fun, but I don't know about safe. Having that sharp of a change might be a bit dangerous. This one here, okay, so we're going downward, and then somehow magically our roller coaster elevates and then starts going upward. So the magic part might be kind of fun, but in reality of our real world, it's a bit confusing. And I don't think that would be very fun or safe. Let's go with not fun or safe. Definitely not safe to like suddenly levitate to another height. That's definitely not safe. So with these, what we're thinking about is we want to be careful of sharp edges. We also want to be careful of jumps. What makes for a fun and safe roller coaster is that smoothness with no jumps, no sharp edges. So consider these roller coasters below. Which ones are unsafe to ride? I would say this one with the sharp turn, because that one you'd be going downward, and then all of a sudden you'd be going upward. That would hurt in terms of a roller coaster. Also unsafe would be this one where we have a jump. This one is particularly dangerous because you'd be dipping downwards and then somehow transported to another height, going downwards and then upward. That part of the ride looks nice, but this whole jumping to a different height without connecting, it's scary. So what we're getting at here is the idea of continuity and differentiability. And even though this first function with the sharp edge is continuous, because I can draw it all with just one pen stroke, we want to be careful of those sharp edges. So to talk about differentiability, which is the idea of taking the derivative, let's write that down, taking the derivative, we want a continuous and smooth function in order to take the derivative. So our function will be undefined when we have jumps and when we have sharp edges.